So we're starting now the lectures for the summer school with Professor Malcolm Perry from University of Cambridge. And what is the most important thing you should know about gravity? Well, black holes.
Well, thank you for that introduction. The instructions that I was given were to give 4 lectures on the elementary properties of black holes. Roberto Emperan will be giving some further lectures on more advanced topics later on. So I'm supposed to start from the beginning. And as Jiri has already told us, history is important in this subject. So let's start at the very beginning. My beginning is earlier than yours. 1783, John Michell. He was a clergyman working in Yorkshire, in a parish of Thornhill. He had previously been a professor at Cambridge, but in those days, if you got married, you were exiled. And so he was exiled up to Yorkshire. But he was the first person that I know of to describe black holes, but his black holes were Newtonian. He essentially knew about the inverse square law and computed the escape velocity from a spherical massive body. And he knew that the speed of light was finite because of the measurements of Römer in the previous century. And he concluded that if you had a body of radius r and mass m, that if r, meaning the radius of the body, was less than 2gm over c squared, where m was the mass of the body, then light would be unable to escape. And from this he concluded that there were dark stars in the universe, things that you'd never be able to see. And this, of course, I think gave him existential problems of one kind and another. Well, of course, this isn't really quite right, but it tells you that there are things which you may be interested in general relativity, and it is general relativity that we need to think about when talking about black holes. So let me deal with conventions first of all. My conventions will be that the signature of spacetime is minus plus plus plus, and my curvature will be defined by del A, del B, minus del B, del A, acting on an arbitrary vector field is equal to RAB CD times VD. So that sorts out my sign conventions. And so what we should do is to move on to the question of general relativity. Well, the way in which I want to think about general relativity emphasizes the causal structure of space-time. In space-time, you can always construct normal coordinates about some point. And if we were just dealing with Minkowski space, then light cones would always look like this. And there's a notion of future and of past. And I'm going to refer to the interior of the light cone, I plus, of this point P, as being the chronological future of P. And then similarly there's an I minus of P, which is the chronological past. And these are the points at which you can reach by some time-like motion from the point P. Sometimes, it is useful to define something slightly different, J plus of P, the causal future. And this is basically the same thing, but including the null cone itself. So that defines, at least locally, what happens in a particular space-time. Now, what general relativity does for you, now let's see, I have to play with these things. Front. That one, the one at the back presumably goes up. Can I press 2 at once, or is that not allowed? Ah. So, what happens in general relativity? The light cones get bent. Curvature of space-time has the effect of the light cones becoming bent, possibly so far that they can even close up. All kinds of strange things can happen to light cones, and that's the nature, that's really what the curvature of space-time is about. Well, let's try and move on to black holes themselves, as opposed to some abstract thing. The first people to consider solutions to Einstein's equations decided that the simplest thing to do was to find the most symmetrical things around. Here I won't quite follow the notion of history, but let's start with Birkhoff's theorem. The idea here is to think about some spherically symmetric space-time, but not impose the idea that it is time independent. We'll see why this is an important thing to do a little bit later. So the idea is spherical symmetry but possibly time dependent. What would the line element look like? Well, the answer is, you would think ds squared is equal to minus some function of t and r, dt squared, plus some function, the same function, v squared of t and r on the bottom, plus some other function of t and r, which I call y squared, into d theta squared plus sine squared theta d phi squared. So that thing is obviously spherically symmetric. If you fix this to be a constant, then of course you just get the metric on the sphere, and its radius will be equal to y. I've chosen these things to be such that the coefficient here is always going to be negative, and that implies some slight limiting prescription to what I'm doing, but it doesn't detract from the basic idea. Now, impose the Einstein equations. Let's make it vacuum Einstein equations. Then you will immediately find that v and y are independent of t. That, in fact, is one of the most simple versions of the uniqueness theorems, which will prove to be central to much of the study of black holes. So this is a sort of first uniqueness theorem. So life is made very easy. You don't have to consider time-dependent situations. And indeed, you can now go and simply try and construct a spherically symmetric but static solution to the Einstein equations. Of course, it's useful to do some calculations. So here is the first exercise that you can carry out. If you have Mathematica on your computer, it will be easy, because you have to compute the Ricci tensor of this metric. If you do not, it will take longer. But remember, Birkhoff, when he did it, did not have a computer, so you know that it should be relatively straightforward. So the first people to do this were Droste in 1915 and Schwarzschild in 1916. It is perhaps a little unfortunate that Droste lost out in the historical battle for precedence here. So, their metric, we all know, well tested in solar system type experiments. I'm going to take m to be positive. If you solve the Einstein equations, this m is just simply a constant of integration. I've chosen it to be positive for convenience, and we'll see what goes wrong if you choose it to be negative a little later on. And of course, m equals 0 is just Minkowski space, which is not going to be so interesting for us. One thing that you should notice about this nice properties, the first is that it has 4 killing vectors. They're kind of obvious here. There are 3 associated with the sphere. And then there's 1 of time translation. And this is the spherical one. But of course, you know that there's something funny going on, because at r equals 2m, there is some kind of coordinate singularity. And at r equals 0, you know that it's not a coordinate singularity. Suppose you compute the Kretschmann scalar. That is R, A, B, C, D, R, A, B, C, D. A scalar quantity built out of the curvature, this blows up as R goes to 0. So you know that you are already in trouble as a consequence of that. Now, send that out there. So what you can't do is press 2 buttons at the same time, apparently. Well, you can, but then nothing happens. Well, what do we do about this coordinate singularity? The answer is invent a new coordinate. These are usually called the Eddington-Finkelstein coordinates. And I'm going to choose an advanced time coordinate to be t plus r star. R star is sometimes called the tortoise coordinate. And it's defined to be r star is equal to r plus 2m times the logarithm of. Well, quite what it's the logarithm of depends on who you are, but for me it's r minus 2m over 2m. And that's because I don't like taking the logarithm of a dimensionful quantity. Some people leave out this 2m and don't bother about dimensions. So then, what happens to the line element in these coordinates? You'll discover that ds squared is equal to minus 1 2m over r dv squared plus 2 dv dr plus r squared into d theta squared plus sine squared theta d phi squared. Now what I want to do is to look at the VR, or equivalently the TR plane. You will notice that if you put theta and phi equal to a constant, and you put r equal to a constant, then as you vary v, if r is equal to 2m, that corresponds to a light-like transformation. So r equals 2m, theta phi fixed, v varying, that's a light-like transformation. Similarly, if you put theta and phi fixed and v fixed, that's also light-like, because under both of those circumstances this thing is equal to 0. So that means that we can draw a picture of what's going on. This is the surface r equals 2m. A long, long way away from r equals 2m, you know that space-time is flat, and so light cones will look something like this. But you know that light cones are going to vary as you move in this direction, and you'll discover that the light cones tip over and look something like that. You might be alarmed by the fact that if you stare at this expression, as r goes to 2m, this thing is tending to minus infinity. So for v to be finite, if this is minus infinity, t is going to plus infinity. But nevertheless, v will vary in that direction. And r goes out in that direction. So what has happened is that the light cones have tipped over, and it's clear that you cannot escape from this region. Well, that's all very beautiful, but you're going to say, the metric you started off with was time symmetric. And if it's time symmetric, how come this thing breaks time reversal invariance? And the answer is, of course, that you could have done something slightly different and chosen retarded coordinates. This is wet, that might not be a good idea. So you could instead have chosen a retarded time coordinate, u is equal to t minus r star, and done a similar calculation. Under these circumstances, you'll discover that ds squared is minus 1 minus 2m over r du squared minus 2 du dr plus r squared d theta squared plus sine squared theta d phi squared. And this would basically give you the time reverse of the previous picture. So here is a surface r equals 2m. U is going in that direction. Since r star is going to minus infinity and u is finite, t is going to minus infinity. And if you look at the light cones, they'll look precisely the opposite. So that is indeed the time reverse of this. This is a region that you must escape from. So we have here something which really does look time symmetric. This surface here is sometimes called a black hole horizon because you can't see it. This is sometimes called a white hole horizon The interesting thing is, of course, that black holes have been observed. No white holes have ever been observed, and so you need to explain how that could possibly come about. We will get to that in a little bit. Well, of course, you might say, well, if you've got some coordinates that display this kind of behavior and some which display this kind of behavior, then perhaps what you should be doing is displaying both at the same time. So let's do that. That was first done by Kruskal in about 1957. Now let's see. Well, that one to go up. That one to go up. And this one to come down. Maybe. Now this, I think, is precisely what they told me not to do, but still, rules are made to be broken. Thank you. Having assistance is great. So let's define the Kruskal. I think I'm going to need assistance to do this. Maybe. Oh, maybe not. Let's see if that works. So, Kruskal coordinates. These are going to be basically the same things as the Eddington-Finkelstein coordinates, but basically just exponentiated. Fine. Maybe that one should go up too because it's now in the shadow. Jean-Michel still seems to be rather prominent here. So, this is e to the minus u over 4m. Big V is e to the plus v over 4m. Make sure I got my signs right. Yes. And outside the black hole horizon, big U will be negative. And V will be positive. And they will both increase towards the future. What is the line element? ds squared is equal to e to the minus r over 2m d big U d big V divided by R plus R squared into d theta squared plus sine squared theta d phi squared. And you will see that this metric is invariant under U V goes to minus U minus V. You will see that U equals 0, V equals, sorry, U, that's right. Let's leave that for the moment. So it's clearly that there's a bit more to the whole thing than we were thinking of, because outside the black hole we've got this relationship. We know that the horizons are going to correspond to U or V equals 0. For fixed, I should say U or V. We'll just leave it like that. And you'll notice that if theta and phi are constant, and either U or V is constant, then these are null lines. So on the face of it, we have a rather complicated causal structure, and the best way to understand this causal structure is to construct a Penrose diagram which explains how the causal structure actually arises. And that will enable us to describe all of the space-time, as opposed to, in this particular case, bits of it in various different coordinate patches. So let's do this explicitly for Minkowski space. So let's start with Penrose diagrams for Minkowski space. Start from Minkowski space in spherical coordinates. The problem with this is that Minkowski space is big. Well, in fact, it's of infinite extent. And that makes trying to show all of the space-time difficult. However, you can conformally compactify it so let's suppose that you take some general metric GAB, then you can construct a new metric GAB hat, which is equal to omega squared GAB. Omega squared, omega is real, so this thing is positive. You don't change the notion of time-like and space-like. But as you know, if you make a conformal transformation, null geodesics map into null geodesics. If that exercise escaped whatever course you did in general relativity, you should try to prove that. Now, what we do is we invent some method of compactifying this. Now, what's where? Well, we'll worry about that one later. Oh, yes. So, The first step will be to invent advanced and retarded null coordinates. U, just t minus r, v is t plus r, and rewrite the metric in the form ds squared is equal to minus du dv plus. Well, it's going to be r squared, so it's going to be a quarter of v minus u, all squared into d theta squared plus sine squared theta d phi squared. Recall that r is positive. That implies that v is bigger than u, and that runs from minus infinity to plus infinity. So far we've done nothing. So the next step is to invent variables which have a finite range. So I'm going to put u equal to tan p, v equal to tan q, and p and q are going to run from minus pi by 2 to plus pi by 2. Pi. No, pi by 2. So q is bigger than or equal to p, is bigger than or equal to minus pi by 2 to plus pi by 2. And if you do that, you'll discover that the line element becomes minus a quarter sec squared p sec squared q dp dq It's not quite what I want to do. Let's get rid of that. I want to get rid of this minus sign. That's better. Minus dp dq plus 4 into u p minus plus sine squared p minus q into d theta squared plus sine squared theta d phi squared. That's better. Conformal compactification is simply the removal of this factor, because it's an overall conformal factor, and as you can see, as the coordinates t and r go to infinity, this thing blows up, but that doesn't change very much. It's basically that property which makes the infinite Minkowski space into this object here. Now what do we do? Well, the thing to do now is to define a new time and radial variables. So I want to define t to be equal to p plus q and r to be p, you get it the right way around, minus q, and then you'll discover that the line element becomes ds squared is equal to minus dt squared plus dr squared plus r. Sine squared r into d theta squared plus sine squared theta d phi squared. And we should ask ourselves about the ranges of T and R, and what you'll discover is that R is positive, and that T plus R is bigger than or equal to T minus R, and that runs from minus pi to plus pi. If you stare at this metric, you'll immediately recognize this as being the metric on the unit 3 sphere. So now what we want to do is to draw a diagram of what this metric is really about. So it's kind of hard to do that. So here is a cylinder. It's a sort of two-dimensional cylinder. It's time, big T, is going to go that way. I'm going to suppress theta because I can't draw 3 dimensions, so this is a picture of theta equals pi by 2. So that phi goes round in that direction. And what you'll discover is that this metric, let's see. If I take the point that is at T equals minus pi, it's going to sit on the front of this surface. And if I take, so this is, if I take the null geodesics from this point, they go round the back and meet again here at T equals R equals 0. But then they keep going and come back to the front and look like this. So what you have is a rectangular region twisted round through 45 degrees. So all of Minkowski's space is mapped into this rectangular region, the interior. Well, that's all very nice, but actually not very convenient if you want to see what's really going on. No, it's a real nuisance. You can't. We haven't had that one. Let's get rid of that one. Oh, you're doing a marvelous job here. Done? Does everyone have this trouble, or is it me? So let's unwrap this region. It looks like that. But let's think about light cones in this region. Well, we suppressed 2 dimensions, but light cones always lie at 45 degrees to the vertical. And we know that because these surfaces are null. So what happens to a time-like line in this picture? Well, here is an example of a time-like line. Just looks like that. Some other time-like lines could look like that, or a time-like line that's doing something interesting could look like that. So these are examples of time-like lines. On the assumption that you don't accelerate something forever, then all time-like lines will start at this point and end at this point. And this is called past time-like infinity. This is future time-like infinity. All time-like lines end at I minus or plus unless continuously accelerated. What about light-like lines? Well, if I say start here and ask what does a light-like line look like, well, it just simply propagates parallel to the light cone. It looks something like that. I've assumed here that, that the angular coordinates are fixed. All null lines start at and end at, well, here you can see it ends on this surface here. This is sometimes called future null infinity. And they will start at past null infinity. So future null infinity is usually called scry or scry plus. Scry plus, the name scry derives from the pre-tech days and stands for what a printer would call script I. And in the past was always written like that, but tech will end up making it look like that. You will find either of them. Past null infinity, let's see, so they start at and end at scry plus. That's easier to draw. They will start at past null infinity, usually called scry minus, and they look something like this. Now, if you have the misfortune to have continuous acceleration, and I can't help feeling that Roberto will talk about that, then a continuously accelerated particle that's time-like will look like that. And that's interesting in a sort of slightly different way, because if you look at this particle and ask, what can this particle observe? Well, you'll notice that the causal past of this observer is this region here. In other words, there's parts of the space-time that this observer cannot see. So this red line corresponds to an horizon for the yellow observer. But I want to emphasize that this particular case can only happen if this observer is accelerated forever. So these observers are usually known as Rindler observers. And this line here is usually called the Rindler horizon. But notice that if you were a typical time-like observer moving along one of these lines here, you'll be able to see all of the space-time if you wait long enough. Of course, if you were at this particular point here, you'd only be able to see what's inside your past light cone. But if you waited, you'll be able to see all of the space-time. So, typical time-like observers can see all of the space-time if they wait long enough. Well, what do you see? If you were an observer watching something in the middle of Minkowski space, the chances are you'd do it with a telescope. And so you'd only see what happened in your causal past. So a typical observer will sit here and their telescope will see what's along a particular null line there. What about these coordinates u and v? Well, this surface here has v infinite, but u, that's just retarded time, will be finite, typically, and it lies anywhere between minus infinity and plus infinity. So Scri plus is essentially a sphere across a real line. Similarly, at past null infinity, this corresponds to v, u being equal to minus infinity, v lying from minus infinity to plus infinity, so it's a good coordinate as you move up and down Scri. So this also is S2 cross R. So, but bear in mind, when thinking about this, whenever you have a sort of Minkowski type region somewhere, then what you see is what happens at null infinity. Remember, you have to take care of the causal properties of the space-time, and that's a universal thing when thinking about relativity. We have undoubtedly all done courses in electromagnetism where the fact that you do things involving retarded time, u, is important. But in many cases, we've all done calculations in which we say, oh, well, infinity is where r goes to infinity, because that takes us to a long way away from anywhere where anything interesting might be happening. Where is r equals infinity and t finite? And I should say this is according to some. Well, that's here. This is a point called I0, sometimes known as space-like infinity. And often, but not always, abbreviated as SPI, but spelt SPI. But remember, that's not a physical place. You don't really have access to space-like infinity. Space-like infinity is a sort of mathematical idealization and has nothing to do with whatever you can observe. Remember, if you're going to make experiments, it's going to be either future null infinity or future time-like infinity that you're going to end up living. Well, that's enough of Minkowski space. In the next lecture, we will move on to deal with what happens in Schwarzschild and other interesting solutions. So let's stop there for the moment.
Hi, thanks for a nice talk. Could we just quickly run over the boundaries and speak about their topologies? Like, what is a point? What is a sphere? What is...
So you want to get rid of these boundaries? Well, the answer is not really, because what you could do is you could ask yourself, suppose, for example, you put some kind of cutoff here. Then you could put a null line here and then ask what goes beyond it up to infinity. But once you've got to infinity, you can't go anywhere. Of course, if you try to do this in cosmological space-times, the situation is different. And so, for example, well, maybe Roberto will talk about this. He will talk about black holes in ADS, where the situation is quite different. And we could talk about black holes in de Sitter if we have time, where again the situation is somewhat different, and there is no infinity of this type. But if you are just simply sitting looking at some black hole, well, in the next lecture I will show you what happens if you just sit and look at a black hole that's isolated in space-time. Maybe that will answer your question.
Thanks.
Oh, yes. Yeah, so someone else has to hear you.
So just a very naive question, because you were talking so much about observers. I mean, I realized that the relevant points are I plus or future time-like infinity, but wouldn't you rather say that if you observe something, it's at some finite time? I mean, infinite time is also like...
well, maybe, but the question is, which time are you talking about? If you go to T and R both large, corresponding to, well, if they're getting large at the same rate, you'll end up here. But if T is going to infinity faster than R, you'll end up here.
Right. But I'm just saying, so what I mean is, rather than taking T to infinity, you would do the measurement at some finite time. So.
Oh, well, you could do that.
Infinite.
So, what you're thinking of, well, I better use a different color actually. So you're saying, well, perhaps I want to do it at some finite T.
Yeah.
So here's an example of something at finite T. So this would be T equals constant.
Right.
And of course you could do that. But then you have to ask yourself what you want to measure. Suppose you wanted to measure, I don't know, you're going to look at what's happening. You have to just look along past your past light cone. That's all you can see. But you might have a record of what happened everywhere to the past of that. So you might have, if you were there, then you could in principle have a record of everything in this region, in principle, but that might not be what you're actually looking at. So the answer is that you really, if you're going to measure something, you need to look at this picture, figure out where you are, and then you'll be able to see what you can see. So always draw a diagram that looks like this.
Thank you for the nice talk. So when you're saying that typical time-like observers can view all of space-time if they wait long enough, are you talking also about the complete space-time, including the boundaries as well, or it's just the inside of the space-time? I mean,
if you were genuinely at I+, then it would be the entirety of the space-time, including scry minus and scry plus. But in practice, you will never be there. You won't get there. You'll end up on one of these green lines or something. If you just have to wait long enough. You could be almost there.